This is Point Nemo, the most remote place on Earth, the furthest you can get from any landmass. It's here that in 2030, a rendezvous has been set with one of humanity's greatest feats of engineering. For over a quarter of a century, the International Space Station has served as our outpost in the cosmos, a symbol of human ingenuity and unprecedented international cooperation. With a construction cost of more than 160 billion US dollars, it's the most expensive thing ever built, and easily one of the most complex. When thinking about the International Space Station, the word masterpiece comes to mind. It is a work of art, a culmination of technical and engineering skill that has not been replicated in any other place. No structure on Earth has to cope with temperature swings of 270 degrees Celsius, nor with being pieced together at 22 times the speed of sound. And yet, in just 5 years' time, the final remains of this extraordinary achievement are going to be driven into the ocean in the most challenging demolition project ever attempted. But why does this extraordinary achievement have to meet its end? And could we not find a way to save it as a testament to human endeavor? To understand that, we'll first have to discover how it was built and what that means for our future in space. The year is 2030, and a specially built SpaceX Dragon is about to set off on its journey to the International Space Station. The Dragon first entered service in 2012, ferrying cargo to the station, with a newer version coming along 9 years later to carry crew. This variant, however, has been specially developed to serve a very particular function. It's equipped with 46 Draco thrusters, small rocket engines capable of generating over 40 kilos of force. A normal Dragon has only 16. Its trunk is twice as long as a typical craft, allowing it to carry 6 times the amount of fuel. That's going to allow it to generate up to 4 times the usual power of a Dragon. Perfect to help it complete its mission to put an end to one of humanity's greatest achievements. Somebody who knows just how incredible the ISS is has served on it twice, in 2009 and 2011. If you look at pictures now of it, it looks like a work of art. Chunks of metal, modules that would fit inside of a space shuttle payload bay, sent up separately to space and then hooked together using robotic arms and spacewalking astronauts to bolt it all together and have it work once it's there. The ISS is not the first or the last space station to take up orbit around the Earth, but none of the others have come close to matching the size and scale of its ambition. And the journey began in 1971 with the launch of Salyut 1 by the Soviet Union, the first ever space station. It was a groundbreaking but short-lived achievement, lasting just 175 days. The first crewed attempt to board it failed, and while a second attempt succeeded, tragedy struck on their return when the Soyuz 11 capsule depressurized while preparing for re-entry, killing all 3 cosmonauts. In the wake of this, Salyut 1 was terminated and allowed to burn up in the Earth's atmosphere in October 1971, less than 5 months after its launch. But despite this rocky start, NASA and the Soviet space program continued to develop crewed outposts in space. Over the next 16 years, 8 space stations were launched, with the US premiering Skylab, its first attempt, in 1973. With each new station, the ambition of what could be achieved slowly grew. Space stations became larger and remained in service for longer periods. The biggest breakthrough came with the USSR's Mir space station. Launched in 1986, Where previous stations were composed of single, monolithic units, Mir was the first truly modular station, being slowly built in stages over the course of 10 years. The US wasn't far behind. In the 1980s, it began developing its own modular station, called Freedom. But while this new generation of space stations promised unprecedented technological advancements, they came at a crippling cost. The Freedom underwent intense scrutiny, and the program suffered multiple budget cuts until it was abandoned altogether. By 1993, as the Cold War ended and Russia's ability to maintain Mir weakened, the two nations decided to come together not as rivals, but as colleagues. And so, the ISS was born. Soon after, other space agencies recognized the significance of this collaboration and joined the program. The European Space Agency, Japanese Aerospace Exploration Agency, and Canadian Space Agency signed up, bringing their technological expertise and resources to the project, transforming the ISS into a truly international endeavor and creating an unprecedented shared commitment to space exploration and scientific advancement. The result of that cooperation is what we see today, a sprawling structure consisting of 43 interconnected modules and elements, covering an area larger than a football field. It's a global effort and a contrast to modern space exploration, which is increasingly fueled by private companies held by the billionaire class, from SpaceX to Blue Origin. Now back to that space station. Everything started in 1998, when the Russian Zarya, or Sunrise, module entered orbit. Construction of Zarya began in 1994 at the Khrunichev State Research and Production Space Center in Moscow. It was manufactured from rolled aluminum, with steel providing strength in essential areas like the docking mechanism. Thermal insulation was provided by a ceramic blanket, and crucially, Kevlar provided the module's armor. More on that later. For power, it was fitted with 2 solar arrays which charged 6 nickel-cadmium batteries capable of providing 3 kilowatts of power. To put that into context, that's about the same amount your domestic oven runs off. In other words, the same power you use to bake a deep-pan pizza was used to operate the fledgling ISS. On top of that, Zarya had 36 steering jets and 2 engines that could make major orbital adjustments, giving the early ISS the ability to move and keep itself steady as new modules were added. If you take a closer look at Zarya, you'll notice something we'll see on all habitable ISS modules. That's this cylindrical shape. That's partly to make it easier to fit into the cargo bay of the space shuttles, which ferried most components into space. But there's another much more crucial reason. Now, just quickly, this is a can of fizzy drink, Coca-Cola in this case. The reason I'm showing you this is because the aluminum can is just about the greatest design in the history of industrial design. And there's a few reasons for that. First of all, it's very efficient. Because it's a cylinder, it uses the least amount of material to enclose a space compared to other shapes, like cubes or rectangular prisms. That also means it's very light. Secondly, the atmospheric pressure inside this is about twice what it is out here, although it could go up to about 6 times that. And it's all thanks to that round shape. It makes sure the internal pressure is evenly distributed. That means there are no weak spots, and the can ends up incredibly strong. The modules on the ISS are actually very similar to this can. They need to be lightweight so they can be launched into space, but also strong enough to resist the forces acting on them due to the pressure differences up there. A month after Zarya came the first US capsule, Unity, which provided the first living and working space and acted as a bridge between the Russian and US halves of the ISS. But it was here that two construction methods clashed for the first time, as the US and Russia had both developed their own mutually incompatible docking systems. The US capsules use the Common Berthing Mechanism, CBM. This system relies on two interlocking rings, one passive and one active. During docking, the passive ring is inserted into the active side, where a series of latches engage to create an initial soft capture. Once aligned, 16 motorized bolts secure the connection, forming a rigid and airtight seal. Meanwhile, Russia had developed its own docking technology known as the Androgynous Peripheral Attach System, APAS. Unlike the CBM, APAS uses two identical, symmetrical docking rings equipped with a capture mechanism inside. This design allows either end to act as the active or passive side, making it more versatile in automated docking scenarios. To overcome these different mechanisms, a special unit known as a Pressurized Mating Adapter, or PMA, was developed. This unit serves as an interface, creating a pressurized tunnel between Russian and US modules. The first PMA was installed between Zarya and Unity, the initial Russian and American segments of the ISS. In total, 3 PMAs were added to the station to facilitate docking with both shuttle-based and Russian Soyuz spacecraft. After Unity, the next major component added to the ISS was the Zvezda service module, which arrived on July 26, 2000. Zvezda was the first fully functional living space aboard the station. It provided life support systems, flight controls, and crew living quarters, making it the true backbone of the Russian segment. A crucial milestone was reached at the end of the year 2000 with the installation of the P6 truss, which housed the first major heat sink panels and large solar array wings. These arrays significantly increased the station's power generation capabilities, meaning the ISS was now ready to sustain life on a permanent basis. On November 2, 2000, the first full-time residents arrived aboard the ISS, marking the beginning of an unbroken line of human habitation in space, which continues to this day. This is what the ISS looked like at that point, which is quite different from how it appears today. To understand how it all works, we'll skip forward to 2011, which marked the end of the main period of construction. But before we do that, what's it really like to live and work up there on the International Space Station? Life on board the space station is extraordinary in so many ways. You're in this place where your body behaves differently. You float and fly in 3 dimensions. The work done there is significant, with astronauts performing daily maintenance, from routine housekeeping like cleaning to more complex tasks like repairing the toilet, fixing a solar array, or replacing batteries that have reached the end of their service life. The same kinds of tasks that must be done on Earth also have to be managed on the space station. To understand the station's layout, let's begin with its orientation. This is the top and this is the front. The part that first sees the 16 sunrises the ISS witnesses every day as it flies over Earth at 28,000 kilometers per hour. Like a ship, it has a port side and a starboard side. This is Unity, the bridge we saw earlier, also known as Node 1. Coming off Unity's starboard side is Tranquility, a functional node that allows additional modules to be connected. Tranquility is also home to one of the most iconic features of the ISS, the cupola. This module, with its 7 windows, gives astronauts an incredible view of Earth, and has been responsible for some of the most breathtaking images ever taken. Coming off the front of Unity is Destiny, the first dedicated laboratory on the ISS. Beyond that is Harmony, another functional node designed to connect more modules. Attached to Harmony's starboard side is the European Columbus Lab, while on the port side we have Kibo, Japan's own research module. At the very end of Kibo is the exposed facility, which allows experiments to be conducted directly in the vacuum of space. But all of that would just be a very expensive tin can if it wasn't for a critical piece of apparatus, the integrated truss structure. This structure houses two critical utilities, the station's power plant and radiators. To build it, 9 truss segments were gradually installed on the ISS, anchored to the roof of Destiny. Over the course of 3 years, solar panels were added to both ends of the truss. Although it would continue to evolve over the next few years, by 2011, the ISS was complete and able to fully realize its mission to push the possibility of long-term space exploration and improve life here on Earth. Back in 2030, the SpaceX Dragon has begun its journey to the ISS on board a specially developed rocket. On a typical mission, after launch, the Dragon begins a series of meticulously timed maneuvers. Around 158 seconds into flight, the main engines of the Falcon rocket shut down. At this stage, it's traveling about 10 times the speed of sound, 80 kilometers above the Earth. A few seconds later, the first and second stages separate, and the secondary engine begins a 7-minute burn, which brings the Falcon and Dragon to low Earth orbit. As this happens, the Dragon's nose cone gets discarded, revealing the berthing mechanism. 9 minutes and 37 seconds after launch, the second stage engines cut off, and 35 seconds later, the Dragon detaches, having reached an orbit where it can begin fine-tuning to align with the ISS, 420 kilometers above the Earth. To put that into context, if you fly from LA to Las Vegas, it'll take about an hour and a quarter. The Dragon will have covered that same distance in just over 10 minutes. When the final Dragon takes this mission, it won't have to climb anywhere near as high. Since 2026, the ISS has been allowed to slowly deorbit and fall down toward Earth. That gives us a clue as to why the ISS needs to be decommissioned in the first place. The altitude the ISS orbits at is very carefully calibrated. It needs to be high enough to experience weightlessness and space-like conditions, which is why it orbits in the upper reaches of the thermosphere. That's high enough to conduct research in a microgravity environment, but there's a catch. There is still enough atmosphere here to create some drag on the space station, which constantly pulls it very slowly back down to Earth. In other words, the ISS may be in orbit, traveling very fast, 28,000 kilometers per hour, but it's not floating, it's flying. Every few months, a rocket visits the ISS to reboost it, which is why its actual altitude varies between about 370 and 460 kilometers, depending on where it is in this cycle. So that's one reason we need to figure out what to do with the ISS. If we just abandoned it, it would eventually fall to Earth, and it could land anywhere. But you might be thinking, why not avoid that problem altogether by operating it at a much higher altitude? Well, that's when you run into a whole world of problems. Operating the ISS at higher altitudes becomes exponentially more difficult. The cost and technical complexity of sending regular crew and cargo missions would be too great. But there's another, much more catastrophic reason it can't fly higher, and it serves as a reminder of the brutal conditions the ISS exists in. Remember the Kevlar armor that wraps the outer casing of the ISS modules? That's to protect the structure from the constant bombardment of tiny meteorites and space junk. The US Department of Defense tracks objects orbiting Earth, so when a large piece of debris, around 10 centimeters or more, is heading toward the ISS, the station fires its boosters and dodges out of the way. But there's no way of avoiding smaller objects, and thanks to the thin atmosphere, these can travel up to 10 kilometers per second, meaning even tiny collisions can have a catastrophic effect. In 2016, an image was released showing a 7 millimeter wide crack in one of the cupola's windows, thought to have been caused by a fleck of paint. Accidents like these are random, but there's another factor that happens like clockwork and places a huge strain on the ISS: extreme temperatures. To explain that, let's look at one of the most impressive buildings on Earth. Building the Burj Khalifa wasn't a challenge just because of its height. Engineers had to find extreme solutions to everything, from preventing it from sinking into the desert sand to ensuring it wouldn't be blown over by the wind. But one aspect that doesn't get enough attention is how it regulates heat in the blistering Dubai sun. The tower uses a range of techniques to reduce heat absorption, including glass panels coated with a special silver lining that reflects sunlight. This prevents excessive heat buildup and helps regulate temperature swings between day and night, summer and winter. This matters because it's not just the people inside the Burj Khalifa that need protection, it's the building itself. The issue is something called thermal expansion. During construction, when the steelwork was still exposed, the Burj Khalifa was recorded as being 36 centimeters taller on the hottest afternoon of the year than on the coldest morning. If left unchecked, that kind of thermal expansion and contraction leads to stress fatigue, which could undermine the tower's structural integrity. The Burj Khalifa may be the tallest building in one of the hottest places on Earth, but its twice-daily temperature swings of 10 to 15 degrees Celsius are nothing compared to what the ISS experiences. The ISS orbits Earth 16 times a day, constantly flying through sunlight where temperatures soar to 120 degrees before plunging to negative 150 degrees in Earth's shadow. The stress this places on the ISS means that, at some point, a joint or weld will fail. And on such a large and complex structure, it's impossible to predict where. It's a reminder of just how precarious life on the ISS really is. It's a super hostile environment, the deadly vacuum of space. You hear it, you smell it, you feel it in ways that training doesn't necessarily prepare you for. Those big thermal cycles, the 250 degrees Celsius shift from sunlight to darkness every 45 minutes, you hear it. It's not big bangs, just a creaky sound, like metal expanding and contracting. Another reminder of the danger came in 2019 when a leak was discovered in the Zvezda module. It came from a microscopic crack in the transfer tunnel leading to the aft docking port, PRK. At the time, the leak was deemed non-threatening, but the rate of air loss increased. And by November 2024, the decision was made to keep the PRK hatch closed during standard operations. Now, when the PRK needs to be accessed, a hatch between the Russian and US halves of the ISS is closed to prevent catastrophic depressurization. Once the Dragon reaches the ISS, it will dock, and the station will begin its final descent. But does the ISS really have to be smashed into Earth in a fireball? In 2022, NASA published a transition plan outlining several decommissioning options, including disassembling the station in space and returning it to Earth in pieces. However, the report concluded the task was too complex, requiring over 160 spacewalks, roughly the same number performed in the ISS's entire history, and a cargo vehicle capable of carrying large components, which doesn't exist since the Space Shuttle's retirement in 2011. So, why not just blast it into deep space? Pushing it completely out of Earth's orbit isn't feasible. We don't have the resources or technology. What about boosting it to a higher altitude? NASA considered this, but the plan ran into countless problems. The ISS sits at the bottom of low Earth orbit, below 2,000 kilometers, where space junk concentration is highest. While the station's armor can handle small debris at its current altitude, the risk of catastrophic collision increases dramatically at higher orbits. A study shows that while the ISS could survive over 50 years at its current height, its lifespan would shrink to just 3.8 months at 850 kilometers. In other words, if we sent the ISS to a much higher orbit, it would just get smashed to pieces, creating a massive risk to future space travel and infrastructure. Again, there's the problem of technology. The SpaceX Starship is currently the only rocket in development designed to deliver heavy cargo to the outer reaches of Earth's atmosphere, but it's not designed to dock at the ISS. Even if it were possible, the immense power of its thrusters would likely cause the ISS to break apart as it began to move. So if it can't go up and can't stay where it is, it has to come down. The Dragon will connect to the ISS at around 280 kilometers, the point of no return. At some point in 2030, the final crew will have visited and retrieved any essential equipment capable of being transported back. Once docked at the front of the ISS, the Dragon's Draco thrusters will perform a series of burns, generating enough power to ensure the ISS re-enters the atmosphere at a high enough speed to guarantee its complete destruction, posing no threat to life on Earth. Shipping lanes and flight routes have been cleared along the path to avoid collisions, and the South Pacific Gyre, the strong currents running through Point Nemo, will keep marine life well clear. As the ISS passes the 120-kilometer mark, it begins to leave the thermosphere, and the show begins. Traveling at 29,000 kilometers per hour, Earth's rapidly thickening atmosphere starts ripping the space station apart. The first things to go are the solar panels and radiators, and shortly after, the modules begin to break apart. The friction of the atmosphere creates temperatures reaching 4,000 degrees Celsius, causing the scattered capsules to burst into flames. A spectacular fireball streaks 6,000 kilometers long across the skies as the biggest demolition job in history melts the aluminum modules. From that huge debris field, only a few small artifacts survive to splash down in Point Nemo. The International Space Station is the culmination of decades of relentless innovation, an achievement built on the hard work of engineers and space agencies constantly pushing the limits of what's possible. Each generation of space station grew more ambitious, more complex, until we reached the pinnacle with this incredible structure. But when all of this is reduced to a few fragments of scorched metal, what will we look to next? NASA is currently backing the development of commercial space stations, such as Starlab and Axiom Station. These projects, along with several others in the works, promise to continue human spaceflight and research beyond the ISS era. However, they're all much smaller in scale and designed to operate as private enterprises rather than in the spirit of international cooperation and human endeavor. Meanwhile, the largest space station currently in operation after the ISS is China's Tiangong, which began assembly in 2021. The age of a single massive international facility may be over, but that's proof of the incredible legacy of this building. The purpose of the ISS was to be our gateway to the stars, to conduct research that would help us go further and for longer than ever before. But we also shouldn't forget that the ISS has always been as much about life down here as it is up there. The mission statement for the International